Kayla. So I've been messing around with the Trombe wall some, and I think I found a way we can do it, at least to get an estimate that makes some sense. It's not the way I was thinking, so let me just go over that and kind of the thought process there. Uh, my idea was to use the thermal analysis simulation and have a concrete wall that was had air behind it and in front of it, and then a piece of glass in front of that, and then an adiabatic surface all around it. And so the idea would be that then run a thermal simulation. This airspace would heat up behind this glass, and that heat would move through the concrete into the interior um, air volume. The problem that I ran into was that, so at first I just tried it without any cuts in here, and then I made turn these into air zones because the idea is supposed to be that uh, the air in here heats up in this airspace because the glass, and there's this little hot box here, so that it gets pretty hot in there, and then hot air goes through this zone at the top, just this hole, and then that hot air then creates a displacement in here that needs to be filled as it moves into this space, and so that pulls air in from the bottom, which is a little bit colder down here, the bottom of the floor, and you create just what's called a thermosiphon, and it just moves around in a circle and um, passively moves the heat from this volume into the space, and that allows us then to take a lot more advantage of the heat in here because as soon as the sun goes down, this is going to cool down and we're going to start losing heat out of here, even if we have a pretty good piece of glass in front of it. So we want to dump as much heat as we can during the day into the space. The problem is that there's no way that I can think of in Climate Studio to cause that air to move passively through these holes. It's just not set up to do that as far as I understand it. And there are ways we could do it. There is this, other programs. I did it. I did it with a graduate student one time in SolidWorks, where we used CFD, which is computational fluid dynamics. It's just another simulation approach where um, you can simulate the movement of air as it heats up. Anyway, so we're not going to do that. But I have another thought that I think will work. So, and it's pretty simple. So I created a ground plane here and a piece of concrete. The concrete really is not even necessary. We just need a surface here. Um, and then I put a piece of glass in front of it. And so the idea is if you want to do this, you would place this. This is your Trombe wall, so you'd make it as large as you want your Trombe wall to be. Though that's something we can talk about. All you're going to see, what I'm doing is just trying to figure out how much heat per square foot hits this surface, and then we'll use that for our estimation, our simulation. So what I did then was I just created a surface on top of that, this piece of concrete, because remember in the radiation map we have to apply materials to the things that we want to have heat bouncing off of, like the ground here I made asphalt, and the concrete mass I made concrete. I don't think that even has an effect here because that's not what the sun is hitting. The sun is hitting the surface that I made that's just on the concrete. By the way, I made it the sensor spacing every 2 square feet because I only made a 20 by 20 foot. So you may want to adjust that if you try this. Each little black dot is a sensor. Black dot. So if I run this, we see that I'm getting on all surfaces. There's only one surface we created. And I'm using the total exposure. Remember we have those, we could say indirect, which is what's bouncing off the clouds, direct, which is direct solar, straight, that's normal to the direction of the sun. The total, we talked about how that's calculated later, but I think that's the best way of, it's just all the sunlight or the sun energy hitting that wall. And so we see that this is the number I'm really interested in, 364 kilobtu's per square foot per year. So every square foot is around 375 um, kilobtu's. And so like this, for example, this is a 20 by 20 foot, which isn't huge. Um, that's 365, let's say, times 400. It's 145,000 kilobtu's, so 1,000 BTUs. It's not a trivial amount, even something this small. So then, um, the next thing, but that's not really going to work because then if we then said, okay, I'm going to say that my concrete wall is going to be getting 365 kilobtu's per square foot per year into the space, that's not accurate because that's just what's hitting the wall. And in perfect situation, all the concrete would heat all that up and then move it into the room. But that's not what's going to happen because we're outside here, and so actually, as soon as the sun goes down, or if it's cold outside, that concrete won't be will be heating up some, but it'll also be losing heat to the space, to the outdoors. So we need to put a piece of glass in front of it. So I did that, and so let's see what effect that has. What I did, I tried a couple things. I just made it like 3 inches in front of the concrete. I don't know. Um, that let's see what it did. So I first made this clear, just the typical clear glazing that we've used before. It has a really high solar heat gain coefficient. About 82% of the heat is getting through it, but has a really low U value. U value of 1 is an R value of 1. I don't know if you think in terms of U and R value at all, but that's very low. You know, uh, fiberglass bat insulation has an R value of about 3.5 per inch, and this is the whole wall is 1, so it's low. But let's see what happens when we run the radiation map. And it's as we would expect. It's like I'm going to name these. This is mass. This is clear glazing. And let's see. Let's go back to this guy. What we're 307, I think, divided by 364. 84. And I think that our glass is about that. 82. So that's pretty cool. That's basically we're saying that. So what I was just doing there is let's see, was that 307? Yeah. So I divided 307 by 364, got 84%, and our glass is saying that 82% should get through, so that's pretty accurate, I would say. Um, Problem with that is that that's going to really help us heat up this because we're going to get like a little hot box thing going on here with this air really heating up behind this glass. But then as soon as the sun goes down, or if it's cold outside, it's going to be less effective, and because it doesn't have any resistance to heat flow. So let's try it with a different piece of glass. So I'm going to look for something that has a high solar heat gain coefficient, but a low U value. And if I look through here, just kind of looks like I can get, so 0.14 is about R7. So, 7 times what that clear glass was. Um, but we're only getting half of the heat coming through. But I think that's a pretty good, oops, wrong one. Pretty good combo. So let's see what happens when we run this. Yeah, so we're getting 307. So we're only getting about, oops, a third, 2/3 of the, let's see, like, actually, I'll just say, it was a U of 0.14 and SHGC of 0.52, I think. So compared to the blank concrete, we're getting oof, less than 2/3 of the heat, but we're preventing a lot of that from moving back out. So the point is, we'd have to just determine um, what we thought was the best combination. One way to do that would be when you actually build your, when you have your project in a state where you can apply, you can do a thermal analysis, then, and the parts of the envelope in front of, make a thermal zone for the Trumbe area and have the exterior facade be whatever the same glazing that you've chosen here, or you could try different ones. Um, and then that would then make the Trumwell part of the thermal analysis in the thermal analysis workflow. But then we could then use whatever number you came up with per kilobtts per square foot, and let's say you had something much larger than this, or whatever size you could say. Uh, and then maybe we just make up some number, like 80% of whatever is hitting the wall, we're going to say is going to be able to move into the building, or we could say 100%, whatever we want to. It's just an estimate. And then we could then use that to offset some portion of the site EUI. It may not be very much. It may be decent. I don't know. You'd have to check and see. But I do think that this then is a reasonable way of, with the tools we have, of simulating a Trumb wall. Not at all saying you need to do it or should do it. I just wanted to answer the question. I thought it was interesting. It's going to be on my list to find a more accurate way of doing this moving forward with some other program, probably. All right. Let me know if I'm, I don't know if this is going to be confusing for you or whatever. If you want to talk to me about it, I'm always happy to. All right. Talk to you later.